Welcome back to lecture 6.1. So in lecture 6.1, we are going to do some exercises with our 3D. So using our three-dimensional equation of state. Now, we're actually going to have this lecture is going to have quite a bit of in-class component, so the pre-recorded section is going to be small, and we're going to do actually a number of examples in class. But let's remind ourselves what our three-dimensional equation of state was. So last time we worked out that it should be dV is beta v dt minus kappa v dp. Let me make sure that's right. It is. Good. Okay, so the first question I have is this thing the same? Is this the same as delta v with beta v delta t minus kappa v delta p? And the answer is no, not at all, right? So what we have to remember what we mean when we mean these things. When I say dt, right, I really mean that this is a derivative, right? And I need to integrate it. And delta v is already, delta v or delta t or delta p, these are already the integrated values, right? They are saying something like, if I had the integral of dv and I had nothing else to depend on, then that integral would be delta v, right? And this was like, from v1 to v2, evaluated from v1 to v2, this is v2 minus v1, right? That's what delta v means, right? Delta v means this difference. But it means I've already taken the integral, okay? So can we do this? Can we go from here to here? Well, sometimes, right? So if we already know, so this is, so the point I want to make, and let me write it down. These are not the same, right? So these are, let me write it on the other side. The answer is this the same as? And the answer is no. But can use this form if we are looking only at small changes in delta t and delta p, right? So if we only had, and part of what we mean by small changes is that everything is linear, right? So that is, beta didn't depend on t, so I could remove it from the integral. V didn't depend on t, so I could remove it from the integral, and I only had these small changes, right? That would say, oh, it's such a small change in p that neither kappa nor v really depended on p, and I could change it out, right? So that's all we mean. And so we're going to do an example. In class on when we can do this, okay? We're going to do an expanding mercury example. But now let's do an example where it's clear that we can't do this approximation, right? So let's imagine instead where beta does depend on t and p and kappa does possibly depend on T and P, right? So there, we're going to need to do our integration properly. Right? And then our delta V really is only going to be when we have integrated, say, from T1 to T2, beta V dt, minus the integral from P1 to P2, kappa V dP. Okay? So that's the more general. So let's use an ideal gas as an example. Whenever I think ideal gas, I think of the most ideal gas, I think of helium, right? So for an ideal gas, beta depends on T, and kappa depends on P. So let's show that. Okay? So let's go back and write PV equals nRT. And well, let's remind ourselves what beta looks like, right? So beta was defined as nope. Just make sure I don't say it wrong. Beta was 1 over V dV dt at constant P. And kappa was minus, let's see, kappa was minus 1 over V, minus 1 over V, partial V, partial P, constant T. Yeah. Okay, so let's work out what those actually are for an ideal gas. Right? So now for beta, we need to look at what V is. So let's write V equals N. So let's be very explicit. V as a function of P and T equals nRT over V. Okay? So let's take partial V, partial T. Partial V, partial T at constant P. Oh. P. So assume our P is constant and take the derivative with respect to T. So that's nR over P. So beta now equals 1 over V nR over P. So just to simplify that and see, so 1 over V is equal to P over nRT. So that's P over nRT times nR over P. Those cancel, those cancel. And we get 1 over T. So let's do the same for kappa. So you can see really B beta, so let me write that explicitly, that beta depends on T, right? It's 1 over T. So if we wanted to do this integration, we would have to put 1 over T in there. Okay? So let's do kappa, right? So kappa is 1 over V, partial T. So let's actually just write partial V, partial P at constant T. So this is V, it's nRT. So we're going to take T to be constant, and we're going to take the derivative with respect to P, right? So we can imagine this as nRT P to the minus 1. So this derivative is going to be minus nRT over P squared, right? So then kappa as a function of P is minus 1 over V minus nRT over P squared. Let's write 1 over V in as P over nRT times nRT over P squared. So that's 1 over P. Okay. So you can see that one and that one. Now, clearly, if we were to take our volume, we would need to take into account if we were to evaluate this integral, we would have to take in the temperature dependence of kappa, of beta, and the pressure dependence of kappa if it were an ideal gas into this. Okay, so we're going to stop there with lecture 6.1, and we're going to do the example for the small changes, the linear changes in class for mercury. Now in 6.2. We're going to go on and we're going to talk a little bit about work, and then the rest of the class will actually be in class. We'll be working on an example.